Welcome to This Explainer. We use numbers every single day to count, measure, calculate. We completely take them for granted. But right beneath the surface of basic arithmetic lies this absolutely fascinating invisible architecture. So today, we're diving straight into the hidden structural rules of the math we use. We are going to look really closely at the literal atoms of mathematics and see how mastering these basic building blocks lets us unravel some incredibly complex logical mysteries. Let's get right into it. To frame our whole journey today, let's start with a massive, foundational question. Are all complex numbers actually just molecules built entirely from simple prime number atoms? Just think about that for a second. If you take any random huge number, thousands, millions, whatever, can it always, without fail, be broken down into a fundamental recipe of primes? Keep that in the back of your mind as we start peeling back the layers of real numbers. Here's our quick roadmap for the explainer. First, we'll look at the prime building blocks. Second, unlocking HCF and LCM. Third, the irrationality mystery. Fourth, we'll do a proof by contradiction. And finally, mixing real numbers.
All right, part one, the prime building blocks.
So let's examine the chemistry of mathematics. When a chemist looks at water, they don't just see a liquid, they see H2O, 2 hydrogen atoms and 1 oxygen atom. Well, mathematicians view numbers the exact same way. If we take a large composite number, say 32,760, and build a factor tree, we can strip it down step by step right into its core prime components. First, we pull out all the 2's, and that leaves us with 2 to the power of 3. Then we pull out the 3's, giving us 3 squared. And what we are left with at the very end is 5 times 7 times 13. We've effectively deconstructed this massive number into a very specific string of prime atoms. And this brings us to an absolute game changer in math, the fundamental theorem of arithmetic. It essentially dictates that every single composite number can be factorized as a product of primes. But the crucial part? This factorization is absolutely unique. It's literally a mathematical fingerprint. There is no other way to combine primes to get 32,760. Sure, you can shuffle the order around, but that specific recipe of primes belongs to that number and that number alone. Now, the ancient Greek mathematician Euclid actually knew about this concept centuries ago, but it was Carl Friedrich Gauss who stepped up and provided the first mathematically rigorous, totally correct proof of it in his famous book Disquisitiones Arithmeticae. Gauss is often called the prince of mathematicians, and honestly, he really showed us just how powerful these prime fingerprints truly are. Moving right along to part 2, unlocking HCF and LCM. So, knowing this prime fingerprint isn't just neat trivia, it is a highly practical tool. By using prime factorization, the rules for finding the highest common factor, the HCF, and the least common multiple, the LCM, become so incredibly clear. Instead of manually listing out dozens of multiples or factors, you just look at the prime powers. For the HCF, you simply take the product of the smallest power of each common prime factor. And for the LCM, you just take the product of the greatest power of every prime factor involved. It's that straightforward. Let's actually see this in action with a quick example using the numbers 6 and 20. The prime factors of 6 are 2 to the power of 1 times 3 to the power of 1. For 20, it's 2 squared times 5 to the power of 1. Now for our HCF, the only prime they share is 2, and the smallest power is 1. So bam, our HCF is simply 2. For the LCM, we take the highest powers of all the primes present across both numbers. That's 2 squared times 3 to the power of 1 times 5 to the power of 1. Multiply those all together and you easily yield an LCM of 60. Literally no guesswork required. And we can even verify this with an incredibly useful shortcut, a sort of golden rule. The product of the HCF and LCM will always equal the product of the two original numbers. Let's check the math we just did. Our original numbers were 6 and 20. Multiply those, you get 120. Our HCF was 2, and our LCM was 60. Multiply those, you also get 120. This golden rule is a fantastic, completely foolproof way to check your work or quickly hunt down a missing variable.
All right, part 3, the irrationality mystery.
Now that we've got our tools, let's step things up and investigate numbers that behave strangely. We're leaving the comfortable, predictable world of integers and neat fractions. We are hunting the irrational number. This is an elusive suspect that totally refuses to be written neatly as a simple fraction, meaning p over q where both are integers. Rational numbers make sense, right? They're ratios. But irrational numbers like pi or the square root of 2 have decimal expansions that just go on forever, never repeating. They cannot be boxed into a neat fraction. But the real question is, how do we mathematically prove a number can never, ever be written as a fraction? Well, before we spring our logical trap to catch an irrational number, we need a smoking gun. And that is Theorem 1.2, which comes directly from our prime building blocks. It simply states that if a prime number p divides a perfect square, let's call it a squared, then that exact same prime number must also divide the root, a. For example, if the prime number 3 divides 36, which is 6 squared, then 3 absolutely must also divide 6. This is a simple but really profound rule, and it's about to be our secret weapon.
Which brings us to part 4, proof by contradiction.
We're ready to build our proof by contradiction. This is a brilliant method where we assume a suspect is guilty, just to mathematically prove that being guilty is totally impossible, meaning it must be innocent. So we want to prove the square root of 2 is irrational. Step 1, we assume the exact opposite. We assume root 2 is rational, meaning it perfectly equals a clean fraction, a over b. And we assume a and b are coprime, meaning they are fully simplified and share 0 common factors other than 1. Step 2, we square both sides to kill the root, rearrange it, and we end up with the equation 2 times b squared equals a squared. Now look closely at step 3. Because a squared equals 2 times something, a squared has to be an even number, divisible by 2. And finally, step 4, thanks to our smoking gun, Theorem 1.2, if 2 divides a squared, then 2 absolutely must also divide a. This logically forces the numerator a to be an even number, which means we can rewrite a as 2c.
So here's where the trap snaps shut. If we substitute a equals 2c back into our earlier equation, we get 2 times b squared equals 4 times c squared. Simplify that down, and we get b squared equals 2 times c squared. But wait a minute. Now b squared is equal to 2 times something. That means 2 divides b squared, and therefore 2 must divide b. The denominator b is also forced to be even. Both a and b are divisible by 2. But remember our foundational assumption. We assumed a over b was a fully simplified fraction with absolutely no common factors. We've just created a literal mathematical impossibility, a contradiction. Because our initial assumption destroyed itself, the square root of 2 simply cannot be written as a fraction. It must be irrational. Case closed.
Finally, let's hit part 5, mixing real numbers. That right there is the sheer, undeniable power of mathematical proofs. But what happens when these newly proven irrational numbers interact with the standard rational numbers we know and love? Well, think of an irrational number like a drop of really strong, dark ink in a glass of pure water. Through similar logical contradictions, we can prove that mixing them always changes the whole glass. Adding, subtracting, multiplying, or dividing a non-zero rational number with an irrational number always results in an irrational number. For instance, 5 minus the square root of 3, irrational. 3 times the square root of 2, completely irrational. That endless, non-repeating chaos of the irrational number always carries through the calculation.
And that brings us to our conclusion.
What an incredible journey from the absolute simplest components to some seriously complex structural logic. Let's wrap up everything we've built today. We've seen how mastering the basics, the prime atoms governed by the fundamental theorem of arithmetic, equips us to navigate high-level mathematics. Those unique prime fingerprints give us lightning-fast shortcuts for finding highest common factors and least common multiples. But much more importantly, we saw how those exact same prime building blocks act as the core structural foundation to build complex logical traps, letting us definitively prove that mysterious numbers, like the square root of 2, are truly irrational. So here's a final, absolutely fascinating thought to leave you with. We've known from mathematicians for a very long time that the list of prime numbers goes on forever. There's literally no largest prime. So if these simple, infinite prime building blocks can unlock the very nature of reality, like proving the irrationality of the square root of 2, just imagine what other hidden mathematical mysteries are out there, waiting for those primes to solve them. Thank you so much for joining me for this explainer, and keep questioning the numbers around you.